this seminar. Okay, perfect. So good morning, everyone. And today we have the pleasure of having Stephen Green from the University of Nottingham. Thank you for accepting our invitation. And today Stephen is going to show us how we can improve the the collection and our understanding of gravitational wave thanks to machine learning, and how this can be applied to mesh filtering data in a way faster way compared to what we have now. So I leave the stage to you, Stephen, and thank you so much for being here with us.
All right. Well, thank you for the introduction, and thanks for inviting me. And yeah, I'm happy to answer any questions throughout the talk if you have any. So please feel free to interrupt. So yeah, the title of my talk is Machine Learning for Gravitational Wave Astronomy. And this is work that I've mainly done with Max Dax, Jonathan Gare, and Jonas Wildberger. Max and Jonas are students, and they've been super helpful and good at this. Okay, so the outline of my talk is, first I'll give just a basic introduction to the problem of estimating parameters based on gravitational wave data. And then I'll describe the deep learning approach that we've been developing, which uses some techniques called simulation-based inference and normalizing flows. And I'll explain what all of that means. And then finally, after we kind of get some basic answers using this deep learning approach, I'll describe how some of the developments we've made, on the machine learning side, in order to really turn this into a viable method that could be used, in production. Okay, so, well, I'm sure everybody is familiar with the basic idea of gravitational wave astronomy, but kind of just to set the stage, the idea is if we have a binary merger, this gives off some gravitational waves, which are then measured in the LIGO and Virgo observatories. And we get some data, so some time series data that looks like this. So this is the time series for the first gravitational wave detection, GW 150914, as observed at the two detectors in Hanford and Livingston. Now, this is a very, loud signal, so you can see right in the data that something's going on. You can see this this in spiral and merger as this increase in frequency and amplitude as the in spiral occurs and the merger occurs, and then this final ring down. But in many cases, it's harder to just see the signal looking at the data. Now, given this data that we observe, the goal of single event parameter estimation is to turn that into a distribution over our beliefs of what the source parameters are. So this is done by comparing against signal models and noise models. And we can, here again for this first detection, we see the inferred masses and the inferred sky position. Now, we don't get just, a single prediction for the masses and the sky position, but we get a distribution because it's unclear. I mean, it's not obvious how to split the observed data into a signal plus a noise. So you can fit it in different combinations, and that's what gives you this spread here. Once we do this for all of the events, we can build up this distribution of event data. So this is all of the observed events showing the component masses and the final mass as a function of time. And really now there's this big catalog of events, and from that we can go and we can try to learn something about populations or cosmology by doing hierarchical Bayesian inference, where we infer at the next level, we infer cosmological parameters, for instance. And the other important important reason to have fast parameter estimation in particular is when we have multi-messenger counterparts. So there's this example from binary neutron star, with the binary neutron star merger, where there was a binary neutron star observed with LIGO, and then using the gravitational wave data, it was possible to triangulate this position in the sky from which it came, and then find an electromagnetic counterpart. So it's important to be able to have fast results in order to do this kind of thing. Okay, now turning to the problem of parameter estimation, and just to set a bit of the notation, we observe this data. So this is again from GW 150914, and we'll call that D. And that is assumed, we have to make a model for this data. And that model assumes that the data consists of some signal, which we call H, plus some noise. Now the signal is that's a function of some parameters, theta. So the theta here would be the 15 parameters for a binary black hole merger. So the masses, the spins, the sky position and orientation, and the time of a merger. And given those parameters, we get an exact waveform. And then, so that's our signal model. We also have a noise model, which is that this noise is residual when we subtract off the signal, is stationary and Gaussian, and it has a particular power spectral density. So when the noise being stationary and Gaussian means that it can be described or its characteristics are entirely described by the power spectral density, or this is an amplitude spectral density. So this PSD or ASD then, it has, it's mostly smooth. There are a few spectral lines, and it does vary a little bit from event to event and from detector to detector. So this is something that has to be measured in some way, maybe estimated prior to the merger by looking at just noise, or by using some on-source technique, such as phase wave. So this has to be estimated and fed into the analysis along with the signal model. So in math, we get our posterior, the probability of some parameters given the data. That's expressed in terms of the, using Bayes' theorem, in terms of a likelihood times a prior. Now, the likelihood is what encapsulates all of the assumptions I described on the previous slide. So it assumes the stationary Gaussian detector noise, and then the likelihood, which is the probability of some data given the parameters, is just a normal distribution with mean given by the waveform, the predicted signal given the parameters data, and variance given by the power spectral density. So we have that, it's written down, and then we can evaluate it, or we could sample from it. The prior, that's typically taken to be somewhat uninformative. And so we assume it's uniform in masses and the spins and the sky position and so on. And given these two, distributions, we can evaluate the posterior up to normalization, and that normalization is the Bayesian evidence. So the task of parameter estimation then is to draw samples from this distribution, the posterior distribution, and that tells us our degree of belief about what the parameters are. Now that's the expensive step though. So the idea here is we usually use a stochastic approach like Markov chain Monte Carlo or nested sampling, and we want to draw parameters from the posterior distribution. Now, the basic idea is we move around in parameter space, we generate waveforms, and we compare to the data at these different points in parameter space by evaluating the likelihood. So meaning we subtract the waveform, the predicted waveform from the data, and we ask what is the probability that this residual is noise with the correct characteristics. And we do this at, we start at some point in parameter space, we evaluate this likelihood times prior, we then jump to another spot in parameter space and evaluate it there, and we can kind of build up this distribution by doing this stochastic sampling. Now, that works really well, and it's the basis for all of the analyses done so far, but it's time consuming because it does require millions of likelihood evaluations per detection. And depending on the waveform model used, this could add up to, just maybe a day up to weeks or even months for the slowest waveform models. So there's a whole industry of building fast waveform models in order to carry out these analyses quickly. So I've already kind of talked about this, but why explore new approaches using machine learning? So the first is this question of speed. So as I said, the model evaluation is expensive, with classical techniques taking from hours to weeks. And we want to have rapid electromagnetic alerts. And the number of events is only going to increase in the future. So here's a plot of the cumulative number of events as a function of time throughout the observing runs. And we can see that this is a little bit out of date. In total, there were about 90. And it's just going to increase. In 04, they've been predicting maybe an event every day or every other day. And with future observatories, we could have, tens or hundreds of thousands of events. So we can't be spending then days on each event if we're at that rate. But there's another, maybe more interesting reason for exploring machine learning is they generally use something called simulation-based inference. And this allows us to move past certain approximations that we usually make in doing parameter estimation. In particular, this assumption that the noise is stationary and Gaussian. So we make that approximation in order to be able to write down that likelihood, but that's only an approximation. And although it's a reasonable approximation, and we're lucky that that's the case, it is leading to some biases in results. Real noise, for example, contains noise transients, so glitches. So a couple are illustrated here in the time frequency plane. And the noise is not perfectly stationary either. And especially for long events like binary neutron stars, you can have the noise level fluctuate, or the PSD fluctuate during the event. And for transients, we can subtract out, and we could model the transient and try to subtract it out. Or, for non-stationary noise, we end up with a non-diagonal covariance matrix, and everything becomes very expensive, so that analysis isn't done. But simulation-based inference actually enables a very natural noise model free type of inference, where we could train our neural networks on real noise and learn to do inference in the presence of this. So this talk, though, is going to focus on the speed and amortization question primarily. So by amortization, I didn't explain what I meant by that. It's basically we are going to train neural networks once, which is expensive, and then just use the same neural network to analyze every event, so that we're amortizing our training costs over all of the detections. Okay, so what do I mean by this simulation-based inference? So we have this likelihood distribution, the probability of some data given some parameters data. And anytime you have a probability distribution, you can essentially do two things with it. First is you could evaluate the probability distribution. So ask the question, so for some parameters theta, what's the probability that the data is D? So we have some data, we have some parameters, and we want to evaluate this probability. So that's evaluating the distribution. And then we can also sample from a distribution. So for us, that means we have some parameters, and then we simulate a data set D. So meaning we generate a waveform and we add some random noise that's consistent with the model. So we can do these two things with a distribution. And the first, this evaluating the likelihood, it forms the basis of what's called likelihood-based inference and the techniques I've described so far, because we evaluate this likelihood all over parameter space and we build up our distribution. So this is called likelihood-based inference, and this imposes certain approximations like the noise is stationary Gaussian. The other thing, the simulating the data, that's called simulation-based inference or likelihood-free inference. And that's what we're going to be using. Now, it's important to note that both approaches are using, they can use the same distribution, but just in different ways. And that's kind of the fundamental difference. So in a bit more detail, what do we do? So we use an approach called neural posterior estimation, which it relies on kind of two things. One is that we have some way of representing probability distributions using neural networks. So this is a kind of magical tool that I'll explain how this works. But the idea is if we have some black box or neural network that represents some distribution, we can use it to evaluate this distribution very quickly or sample from it very quickly. So again, I'll explain how this works. But it's amortized in the sense that, if we have it, this distribution trained, we can just plug in new data and then draw samples for that new data. And I'm going to always denote a neural network distribution with the letter Q just to distinguish it from the true distribution P. Now, neural networks are usually initialized randomly, and then that would be useless for parameter estimation. You want to train it to become a good approximation to the posterior. And this is where the simulation-based inference comes in, because we train it based on simulated data. So we feed it data and we ask it to try to reproduce parameters, and we train it to do this. But we don't actually, have to evaluate likelihoods, and we don't have to use any actual posterior distribution. So that's kind of a really neat fact, that we can train this to become a good approximation to the posterior without having to use any posterior samples. And again, I'll explain how this works. And when we're done, we can think of this Q as some surrogate for the posterior. So that's really the goal. Are there any questions at this point? I've been just talking a lot, but I can also move on if there's no questions.
Well, I have a question, but I guess you're going to answer it in some slides. It seems that you are creating this surrogate for the posterior, and as an idea, it's fantastic. But all the parameter estimation that you do with the usual Bayesian inference also has to preserve the sensitivities, these high good quality matching. So there will be, even here, I guess, some kind of method ad hoc to preserve that kind of good sensitivity, right?
So it's to preserve. I didn't quite hear what you said.
So basically, you have a certain sensitivity that you have to you want to reach, right? Certain number of digits of matching between your models. So I guess also in this approximate method, there is some way to preserve that.
Yeah, I mean, you're always, if you do a surrogate going, usually people have these surrogates going the other direction, where you try to, simulate a waveform and train a neural network maybe, or whatever technique you want to represent this waveform model. So H as a function of theta. And you can measure some sort of, you have some metric like the match to see how well, that performs. And that's a great question, because when you're using a neural network, you want to make sure that you can trust it. And that is going to be the final part of my talk. I'm going to explain how we can verify that everything we do is perfect and there are no problems.
Okay, great.
I'll come to that. But yeah, you're going to basically be checking it in some way. But yeah. So now turning to this, basic approach, how do we get this Q? I already said it was this magical tool, but it's actually called a normalizing flow. So this is an idea that was invented by the computer scientists a few years ago, and we're going to take advantage of it. So the idea is we want to represent this complex conditional distribution. So this probability distribution can have, huge amount of structure, and we're going to represent it in terms of a mapping from a much simpler distribution. So that mapping we'll call F. And the idea is the simple distribution we just take to be standard normal. So that's a distribution we can very easily sample from. It's like the simplest thing you can think of. And then F is some way of, it's this function that takes this normal distribution into the distribution that you want. So I've shifted the problem kind of into the F, but I'll explain how we construct that. And the idea then is, if you want to sample from Q, you sample from the normal distribution, and then you apply the mapping. And the mapping will be very fast because it uses neural networks. And if you want to evaluate the density for some theta, we use this formula, which is the change of variables rule on probability distributions. And F has to have the properties of being invertible and having a simple Jacobian determinant. And that means then that we can evaluate the right-hand side of that equation. So because it's invertible, we can work out this F inverse of theta, so essentially mapping it over here. And then we can evaluate the normal distribution on that. And then we have this det Jacobian factor, which is also needed in the formula. So once we have this F with these properties, then we can very quickly sample and evaluate the density. And we need to have both of those. We need to be able to evaluate the density also to train it. So sampling is for sampling and evaluating density is for training. Now, how do we get this F to have these properties? So by the way, F, I put a subscript D because it depends on D. That's how you make it a conditional distribution. Okay, so it has to be invertible and it has to have a simple Jacobian determinant. And there are various ways to construct this. And the technique we'll use is called a coupling transform, or a sequence of coupling transforms. So a coupling transform takes all of your parameters, so your 15 parameters, and holds half of them fixed, and then the other half transform, element-wise, conditional on this first half and the data. This shouldn't be an S, it should be the data. So when you do this, then if each of these CIs, which are these element-wise, or these component transformations, if each of these is differentiable and has an analytic inverse, then the whole thing's invertible. Well, it's obviously invertible that, the fixed components are obviously invertible, and these CI, these transformed ones, are also invertible by assumption, then the whole thing's invertible. And it also has a simple det Jacobian because of this diagonal structure that we've set up. So the det Jacobian is just the product of the derivatives of these CIs. So this is a way of constructing a coupling transform. And the idea is we'll do a whole sequence of these coupling transforms and build up a more complicated mapping in that way. And then the whole transform would also have these properties. Now, the particular coupling transforms that we use, so these are the CIs, we use what's called a spline flow. This is, again, invented just a few years ago. And the idea is it's defined by these knots. So it's a function that takes one parameter into another one. It's defined by the position and derivatives at these knots. And these, in turn, are defined by the output of a neural network. So it's a bit complicated, but the idea is we take a neural network that has input the data and the untransformed parameters, and it outputs the position and the derivative of at these knots. And then between the knots, it's interpolated using a rational quadratic spline. And then the whole function here is clearly got an analytic inverse because I just drawn it on, and it also is differentiable by construction. So this isn't super important to know these details, but this is just to give you a flavor for what goes into it. And we don't code this up ourselves, but this is just kind of off the shelf. So the whole structure then is we have these normal variables, 15 of them. We permute them into a random order. Then we apply this coupling transform where we hold half the parameters fixed and half of them are transformed under the spline, which is right here, where the spline depends on the untransformed parameters and the data. And then that gives us, a new set of parameters that have been transformed. And then we just repeat this a whole bunch of times until we get to theta, the parameters we want in the end. And this whole construction is made out of neural networks, which means we can take gradients with respect to all of the network parameters. And then if we specify a loss function, we can train it to give us whatever distribution we want. Okay, now how do we train it? That's the other question. So we want the Q to become a good approximation to the Bayesian posterior, and we have to specify a loss. So what would be a natural sort of loss function to pick? So this is the function that will ultimately take gradients of to determine to train the network. So what we do is we take the KL divergence. This is just a divergence on, or like a sort of a distance on the space of probability distributions between the posterior and Q. So if this thing was 0, then the posterior, I mean, then Q would be exactly the same as the posterior. So we want to minimize that. And we also want that we want to minimize this for all possible data that we might encounter. So we take the expectation value over the data distribution. So that's a very sensible loss function. Now, just expanding this out, this is just writing down what the KL divergence is, and the expectation value here. It takes this form. But this isn't actually a very convenient expression because it's extremely non-trivial to evaluate this, and we're still a little bit stuck. The reason why we can't evaluate this is what we would like to do is evaluate this, or what's normally done is we want to evaluate this using a Markov chain, or sorry, using a Monte Carlo approximation. Sorry. So the idea would be we sample from P of D, which I don't know how to do. And then we sample from the posterior here, this P of theta given D, and then we evaluate this log of P over Q. Now, sampling from both of these is very expensive and it's not very feasible. But what we can do is we use Bayes' theorem to reorder these integrals. So we replace P of D times P of theta given D by P of theta times P of D given theta. And now we're in great shape. And because we can really train with this, because we can, writing down this Monte Carlo approximation, the idea then is we draw some parameters just from the prior, which is super easy. And then we draw the data from the likelihood distribution. In other words, we simulate data. So we generate training data by sampling data from the prior, then simulating a signal plus noise, and then we just plug it into the Q and we evaluate this distribution Q. And we've already explained how we can do that because the flow has been set up in a way that we can evaluate that. So in practice, we have these batches of maybe a few thousand simulated theta D pairs, and we evaluate the loss on those. There should be a 1 over n factor out front here. We evaluate the loss on those, and then we take the gradients of the gradient of the loss with respect to all the network parameters and move down that gradient. We just keep repeating this until it gets trained. Now, just some initial results based on doing that. So we take maybe 1 million pairs of parameters and data, and then we train the network, and then we plug in real data, and then we get our posterior in seconds. So this is comparing some results using DINGO, which is our approach, deep inference for gravitational wave observations, compared to LAL inference, which is the normal approach that people use. And you can see that these are in very good agreement. It's not perfect yet, but that's what the rest of my talk is about, how to improve this. But you can see, obviously, it's getting for the most part, it's getting the correct answer. And what I really want to stress, though, is we didn't plug in any distribution that looks like this. All we said was, here's a whole bunch of pairs of parameters and data, and try to learn what the parameters are from the data. And you have the freedom to give a probabilistic answer. So then it gives the posterior distribution. It's kind of the intuition behind the whole thing. Okay. Any questions right now? Or I'm going to next move on to how to improve the results. Nope, good. Okay, so next, how do we improve the results? How do we do things like take into account changing detector noise, which I didn't talk at all about that yet, and how to really improve training. And we developed an approach using symmetries, which improves training. And then finally, this question that always gets asked, which how do you trust the results? And I will discuss that. So the picture you should have now is that we have this flow, taking normal parameters into true parameters, and this flow depends on the strain data. There's this embedding network here, which it just essentially compresses the strain data, and we train it at the same time as the flow. Now, what about the noise? I haven't mentioned that. Well, using this whole approach it's very simple. We just kind of plug the noise into the embedding network along with the data. And if we augment our training set with noise fluctuations, then the network will just learn how to interpret this PSD that we're providing it along with the strain data to give us the best posterior possible. So we just feed in the estimated PSD along with the data, and it figures out how to use it. And how do we make a data set of PSDs? Well, we can either at the end of an observing run, we can just have a whole collection of real PSDs that we estimate during the run. Or also we've developed an approach with a student, with Jonas, to forecast future PSDs based on distributions of PSDs from previous runs. So the idea for 04, upcoming run, is we would forecast a whole bunch of PSDs. We would put them into the training set, and we would simulate data with different PSDs. And then when we want to do inference, we provide the PSD along with the strain data. So, and that's enough to take into account the noise fluctuations. Now, one of the problems we encountered early on, maybe a couple of years ago, was that that we weren't able to achieve the results we wanted because the network had trouble interpreting data that arrives at different times. Now, I've plotted kind of 6 different waveforms here. And if you look at these waveforms, they all look quite different from each other. These are in frequency domain, so this is how they usually look in frequency domain. And they all look kind of different from each other, but in fact, they only differ by having different times of arrival of the data in the detector. These have different merger times, ranging from minus 0.1 seconds to 0.1 seconds. So this is roughly the light crossing time of the Earth. This is, well, it's the resolution of our detector and of our detection algorithms. And the reason that the data looks so different is because in frequency domain, the time shift corresponds to multiplication by e to the minus 2 pi I f delta t. So you get this frequency dependent phase shift, and it ends up looking like this. Now, the problem we had was, our prior contains, all these different merger times, because there's this uncertainty. We have to infer the sky position as well as the overall coalescence time. And this all adds up to time shifts in each detector of about 0.1 seconds. Now, the problem was, we found that the network was basically spending all of its resources trying to interpret these different arrival times, and then had nothing kind of left over for inferring the rest of the parameters. But we knew intuitively that this is trivial. We understand these time shifts. We know what they mean. The network shouldn't be struggling with this. So we came up with this idea to incorporate this knowledge into our training algorithm. And this is we called group equivariant neural posterior estimation. Actually, we generalized it quite a bit, and we published a paper in a machine learning conference about it. And the idea is to iteratively transform to standardized data. So if we knew what the true detector time was, the true merger time, what we could do is time shift the data to have t equals 0. So it would be in the standardized form. And then the network would never have to worry about doing these time shifts, and it could focus its attention on the other parameters. But we don't know what the true time of arrival is, because it's one of the parameters that we want to infer. So that's kind of this loop, and we came up with an iterative method to get around it. Now the idea is, instead of learning the q of theta given d, we augment it, and we also provide an estimate of the detector coalescence time. And if we tell it what this estimate of the time is, then we can equivalently provide the data which has been time shifted by that amount. So that's allowed because we're providing the same amount of information. Then, so the idea is we time shift the data by minus our belief about the detector time, and then if this was a good approximation, then the data would be standardized, and it would be in this simple form. Now,
sorry, Stephen, may I ask you a question? Sorry to interrupt. I'm just trying to understand. Let's say that I have my data, and what you are saying here is that you also provide the time of arrival.
Yeah.
So my question is, if you have the data,
I
mean, I guess that you can go into your data and try to use your, I don't know, something else to get this time, but this would not slow down the entire process. Like, how can you give for each data the precise estimate for the time of arrival or the time of merger in an algorithm?
So it's when you have, so this is something you do at inference when you have your data, right? And you want to figure out what is the time of arrival. So if we can start with some estimate, it doesn't have to be super accurate, then we can time shift our data by that amount, and then we then infer our parameters theta, which are going to be approximate because this time shift wasn't super accurate. But those parameters include among them the time of arrival. And then that gives us a better estimate of the time of arrival. And we plug that in, and then we measure a new time of arrival. So we keep kind of iterating this, and it converges to the correct answer.
Okay.
And does that make sense?
Yeah, no, this makes total sense. The thing that I don't understand still is the iteration 0.
Yeah.
So the first estimate, how do you give it? Because it has to be, right? It has to be in an algorithm.
Good question. So the first, to start it, we have another neural network that's just trained to estimate the time of arrival, but it's not super accurate. So, but it's better than nothing. So,
but doesn't need to be, because you just need to time shift to then do all the iteration with the full. Okay, now I understand. Okay.
Yeah, that's it. And then what you're seeing here is this process happening. So we start off with a rough estimate, and then in about 30 iterations, it converges. I mean, all the parameters converge to the right answer. So it does multiply your inference time by about 30, but we're going from under a second to maybe 20 seconds. So that's not too problematic. Now, this sampling is if in effect Gibbs sampling. We basically alternately sample in T and in theta, and then we converge to the true answer.
Stephen, can I ask you a question here? So it makes complete sense what you're saying, but I'm wondering about if there couldn't be different basins of attraction, meaning you could have different compatible values for the time and the parameters.
Well, you have a distribution. I mean, it's the distribution over the parameter over the time of arrival is typically not very complicated, but that would definitely, it could definitely slow down the convergence if we had a very complicated distribution over the time of arrival, but doesn't seem to be the case. I don't know if I can.
Right. So you're saying that empirically this does not happen, although in theory I don't see why it wouldn't be possible.
Okay, so there's a few details I've kind of glossed over, but I mean, so there's a hat on this TI, right? And so this isn't exactly the detector coalescence time. And it really, what we do is we have to, we infer the TI without the hat from this Q. and then we have to blur it. So we've said it, we have to like add some random noise. Typically, we blur it by about 1 millisecond. And then that's what we plug in to this distribution here, this TI hat, that's the blurred one. And if we don't blur it, then this give sampling will get stuck. It won't move anywhere. We have to have some spread for it to end up actually covering the parameter space. I'm not sure if that entirely answers the question, but if we make the blurring kernel larger, then it will jump more and it will cover, any sort of, issues like this. But yeah, I mean, it does rely a little bit on the distribution not having really disjoint modes. Yeah. Does that answer your question?
Yeah, I think it does. I mean, this could be an unlikely situation, but I was wondering if you had even found it in the kind of cases you were trying, but maybe it's unlikely. I don't know. I was just wondering.
We found that if we don't take the blurring kernel large enough, it can take a lot of iterations sometimes, like 500 iterations or something like this, which does slow it down a little bit. So there's a kind of a trade-off. You want the kernel to be large enough that you cover the space properly and it converges, but you want it to be small enough that you're not faced with widely shifted data appearing here. So it's a trade-off between how well you want to converge versus how standardized you want to make the data.
Mm-hmm. Okay, I think it helps. Thanks, Stephen.
Yeah, this is the most complicated thing. I mean, it's always tricky to explain this approach, but So now we have this picture where it's kind of iterative, and you take these from the parameters, you get the time shifts, and then you kind of iterate like this. So now we get much better agreement. So we put all this together, and here's GW150914. And you can see like these curves for Lal inference in blue and Dingo in orange are just basically right on top of each other. And yeah, so that's where we're about 1.5 years ago. We've in fact improved it quite a bit since then. And the direction we've really gone now is how can we trust these results? So one problem is, the observed data might not precisely match the training distribution. So the waveform that you predict, that your signal prediction is not going to be exactly the same as what nature sends at us, because we use models that are approximate, and also the noise might not be exactly the same as what true noise is. So how do we know when that's happening, and how do we correct for it? And also these checks that I've showed you so far, we're always, cross-checking against standard samplers rather than, doing a fully kind of independent check. And so if we have to always cross-check against standard samplers, what are we really gaining? Right? Okay, so how do we establish trust? So what we do is we actually do have this likelihood. And I think in the interim, before people fully accept these approaches, we can use it to check our answers, basically. So we have our density, which Dingo is giving us, suppose it gives us a density in orange, but the true density is in blue here. Then what we can do is do importance sampling, where we evaluate the true likelihood times prior at that point, and assign a weight to each of our samples, an importance weight by weighting the true distribution over the proposal. So we take Dingo as a proposal, and then we calculate this weight. And reweighting these samples, it also gives us an effective number of samples, which it depends on the weights, the variance of the weights. So if all the weights were 1, then our distribution would have been perfect to begin with. But in general, that's not going to be the case. And then we can calculate an effective number of samples, which effectively measures how well we did. And then this also gives us an evidence calculation. The evidence is very easily calculated. It's the mean of the weights. And yeah, so for example, so we have this event 15, 10, 12, where maybe we didn't do too well, um, because the network's not perfectly trained. When we apply the importance sampling, it turns it into exactly matching result with Lau inference. And this gives us this sampling efficiency, which is the ratio of the effective number of samples divided by the original number of samples. And in this case, it's 12.5%, which is quite high compared to what you get using MCMC. It's a few orders of magnitude higher. So it gives us a result for the evidence, moreover, that's about one order of magnitude more precise than the standard methods give us. So this is important for model comparison. Yeah, and I mean, this is also the other nice thing is that this whole approach is extremely parallelizable, because I can just evaluate these likelihoods all at the same time. And with this high sample efficiency means I don't really need that many likelihood evaluations to get a decent number of effective samples. With the neural importance sampling, we also have this nice characteristic that it tends to work well because we have a very good proposal, and also the fact that we use this forward KL loss means that we tend to produce broader rather than narrower distributions as the proposal. And this means that we have to downweight samples, but we're not missing any modes ever. So this can be so that kind of guarantees that it works properly. So this can be checked by plotting the proposal density against the target density. And we see that we don't see many samples that get upweighted. So this area is pretty empty. We do see a bunch that get downweighted, but that's not nearly as problematic as ones that get upweighted. One of the most interesting things to come out of this is, we did an analysis of 42 events from the O3 catalog, and we're for each event we're giving the evidence and then the sample efficiency that we measured, and this is for 2 different waveform models. And we found that some events had kind of low sample efficiency, like this one over here, like just 0.1%, 0.4%, meaning it didn't work very well. But then when we went back, what we realized was many of these events that had low sample efficiencies actually had been flagged for having data quality issues, like glitches in the data, or in the case of this event, it wasn't clear whether there was more precession than can be properly handled by these waveform models. So what it's really doing with this low sample efficiency is it's flagging problematic events, because this would be expected if the data if the data was out of distribution, then the network wouldn't properly know how to interpret it, and because it's never seen it in training. And then when you calculate the true likelihood times prior, you find that it's not proportional. So that ends up being a flag for problematic data. And Max, really pushed this to an extreme level, where he took data for 150914 and then generated a posterior for it, and then by using gradient descent, he was able to generate fake data. So starting from noise, he trained fake data to give the same posterior. So he tuned the fake data. So this data has nothing to do with 150914, but it gives the same posterior using the neural network. But he found then, when he importance sampled it, that the adversarial data had like 0.006% sample efficiency. So this just really flagged it as being completely fake data that had tricked the network. So that was kind of a fun example. So just to conclude then, I hope I convinced you that we can get accurate inference for binary black holes in seconds, and this will be really useful for enabling rapid alerts and also analyzing huge numbers of events with as complicated or as many waveform models as we want. So this is really going to enable us to do new analyses that were too expensive before. And there's a lot of people working at the AEI now in our group trying to do this with new models. techniques using symmetries or equivariances can really improve learning. And also this using importance sampling can be used to validate, correct, and results, and also identify these failure cases. Now, the outlook going forward is, I want to move into that second part that I highlighted at the beginning, using the simulation-based simulation-based inference to go beyond likelihood-based accuracy, by say training, for example, with realistic noise, and also, applying to other, problems like populations and cosmology or LISA inference. All right, thank you. Happy to take any questions.
Many thanks, Stephen, for a very nice and interesting talk. So now we have some time for questions. Feel free to raise your hand or just unmute yourself. I see Carlos Enz. Please, Carlos.
So hi, and again, Stephen, thank you for the very nice talk. So I was wondering about this curious example that you've shown us, where you generated, it was generated fake data that managed to get the same posterior distribution as the GW 150914. So why? I mean, do you have a clear understanding why this fake data gives the same posterior distribution? So what are the properties that it should have in order to have that degeneracy? And if you'd look at say this in terms of a time domain, I mean, does it look like a very different waveform? So what is it? I'm just wondering.
Well, so I mean, that is, the last part is a very good question, because we've actually never even tried doing the inverse Fourier transform to look at it in time domain. So I don't know what the answer to that is. But we haven't actually looked at the characteristics of this data much. I mean, you can see just from this image, it does have some kind of oscillations on similar timescales, but they're at different spots. I mean, I don't know really what that means exactly, or different frequency scales. I meant is frequency domain. I mean, adversarial examples are kind of a standard problem in deep learning, and I mean, I can tell you how it was constructed, which was we started with random noise, which obviously then gives a random posterior, and then we train. Usually, when you use gradient descent, you train the neural network parameters to give you the answer you want, to give you the loss function, to minimize the loss function. But instead, we trained, we tuned the data, which you can also take the gradient with respect to the data to train the posterior to match. But I don't have any way of interpreting this at this point. But it is a kind of a good question. I haven't thought about it. I will ask Max to take the Fourier transform.
Thank you. It's very curious indeed. Thank you.
Are there any more questions? If there are not, I never worked myself with neither neural networks, neither Bayesian inference. So I apologize if my question is trivial. But so all of these applies very well in principle, in GR. So my question is, if you add more, if you would take any modified theories, this would sometimes just add some extra parameters that you have to take care in your theta, and then we give you some other data and all. It's just that. But I'm thinking if theories that give you other modes, not only these 2 degrees of freedom that GR has, if that would be a problem, or if it would be exactly just another data in your model, or if you should take care also of your waveform model, and then it would trick a bit and make this a bit less easy to use.
Yeah, I mean, I think the approach applies to any waveform model, whether it's as long as you have your H of theta, it should work. And people are, that I'm working with are trying to use this to analyze deviations in the ring down, for example, in general relativity by adding some extra parameters. But but as far as like extra modes, well, those would be reflected. I mean, those, wouldn't be measured directly by LIGO and Virgo, as far as I know. So you can't do anything about that. That's that's out of the question, I guess. But if the extra modes carry away energy, then that would obviously impact the waveform seen in the plus and cross modes. So I mean, you're kind of faced with exactly the same issues you would be for ordinary Bayesian inference with modified gravity theories. But the advantage of this approach is that these analyses might be considered too expensive to do on every event using standard approaches. But now we don't really care about that as much, so we can go ahead. Like in the LVK, they do all these TGR analyses, for example, where they vary one ppn parameter at a time during the inspiral. And so if you, I don't know, if you have 10 of these, then you have 10 times as many analyses to do as the ordinary one, which they do it, but it's really expensive. So this is something that can be sped up using this technique. It really to test.
But still, the system will not know about this, for instance, extra mode. So it might adjust the parameter of your inference in a way that satisfies your probability. Basically, it's just you will never know, right, if there are these extra modes, because
if you can't see them directly, I mean, it's just a problem that any technique is going to face. You can only try to do inference on the basis of having some model, some h of theta for your modified gravity theory.
Yes. Yes, using the GR waveform, it will just reshift the values of the parameter you will obtain in order to be as much as accurate as.
Yeah, I guess another thought, kind of, if suppose your theory of GR was not correct, and there were some deviations, then I think this important sampling step might sort of indicate that, because it would have not seen the GR waveform. I mean, it would not have seen this modified gravity waveform during training. It would have only seen GR waveforms, and then that so in a sense the modified gravity waveform would be out of distribution, and it might flag it in that case if it's far enough away, and if it doesn't overlap too much with a GR waveform.
Yes. Okay, thank you very much. Is there some final questions from the guys in the audience? Well, I don't see any, so a big round of applause for Stephen. Thank you very much for your talk. And I hope we'll see you soon.
All right. Thank you again for inviting me. Bye.
Bye. Have a nice day.
Bye. Thank you. Thank you, Stephen.
Bye,
Take care.
everyone.
Bye, everyone.